Okay, so we have to think of carboxylic acids as proton donors, acids. And then if you do that, and you think, where am I donating that proton? Proton being positively charged, that thing will gain a positive charge, that thing will gain the H. That's what you need to do. So the reaction of benzoic acid, which looks like a benzene ring with a COOH off of it, and sodium hydroxide. So who's going to gain the proton here?
Na.
The Na gains the proton?
No, the OH.
The OH gains the proton to form water. You could say that the proton donor is sodium hydroxide, but more specifically it's the hydroxide part of sodium hydroxide. Okay, so that forms the water, the HOH, and then we end up with benzene ring with the COO minus and an Na plus. So that would be called sodium benzoate. Okay.
So if it's like an ion and has a negative, you just change it to 8?
Yeah. Which might have been, no, that was different, in the Sunny D. Was it benzoate?
I think so, because you said the other one.
Yeah. I can't remember if it was that or an ester, which we're about to learn. Okay, the dissociation of ethanoic acid in water. So CH3COOH plus H2O, funny little arrows of the back and forth arrows, and you're going to get CH3COO minus and H3O plus, because the water has gained a proton. Okay, so any questions on that? Because we just did it on the board, it's not any different. Okay, the reaction of ethanoic acid and ammonia is a lot harder. So CH3COOH and NH3. What is going to donate your proton? Or, yeah, sure. What is going to donate your proton? Who's the proton donor? The acid. So, in this case, ethanoic acid is going to donate the proton. Who's going to accept that proton? There's the proton. Ammonia. What is ammonia going to become after it's donated, or after it's accepted that proton? Ammonium. So NH4 now. Do you see where I get the 4 instead of the 3, everybody? And that NH4 is positively charged. Do you understand now why it's NH4 plus and NH3? And the difference between them? So in Science 10, when you were naming, you would have just named ammonia and named ammonium and learned that that was that, and you kind of looked it up and those are the symbols. But now I hope you understand why it's NH4 plus and NH3 neutral. Yes?
So we get that NH4 exists, but how does it work? Because N has 5 valence electrons, how do all the H's properly attach?
Okay, so hold on, let me finish this. And you get the CH3COO minus. So Leaf is asking what's happening here. So in this molecule you have nitrogen with 1, 2, 3, 4, 5, if I'm drawing the dot and cross diagram, and the hydrogens shared, shared, shared. Did you hear that? That free proton, not very stable. It is incredibly attractive to a lone pair, like it was on the water. Okay, can you see a lone pair? Do you know what a lone pair is? Megan, where's the lone pair? On the top of? The nitrogen. See that? So, you know how this shared pair was like one of the electrons came from nitrogen, one of the electrons came from hydrogen, and they share a pair of electrons, yes? Craig, put your phone away. Okay, thank you. You know what that's a normal covalent bond. This is different, it's called a dative covalent bond. And that nitrogen's lone pair on the top there, that proton is attracted to that lone pair, and they share a pair, but both of them came from nitrogen. It's not an X and an O, it's an O and an O. Whereas the rest were one from each, one from each, one from each. And that's called a dative covalent bond. Okay? And they exist quite a lot, actually. So it's still a shared pair, but just they didn't come from one valence electron each. And now hydrogen's satisfied because it has a full outer shell. Nitrogen's still satisfied, it has a full outer shell, so it's very stable. But it's just not your traditional shared pair of electrons. Okay? Good question. And if you counted all the electrons, you counted all the protons, you'd have one more proton and electron, so the whole molecule is positively charged. Okay, is there another thing on, is there a D?
You created
I created a D for you two boys. So for you two boys, I said iron and pentanoic acid, and you should get hydrogen gas and iron pentanoate, where iron pentanoate looks like this, Fe3 plus, and a pent is going to be CH3, CH2, CH2, 1, 2, 3, 4, 5, and I will need 3 of these. You know why I made you do that? Because when I did almost an exact example on the board, you guys were working on these questions. Right? You had extra time to then figure out what we were figuring out earlier. Okay. All right. So on to, or back up to where it says esterification. And then that leads us into the ester unit. Maybe, if I can get up there. There we go. Okay. Okay. Esterification is making an ester, which, by the way, is the next functional group that we're looking at. So we've done alcohols. We've done carboxylic acids. Now we're going to do esters. In order to make an ester, you take an alcohol and a carboxylic acid, and you do a reaction called an esterification. Not a neutralization, not a single replacement, but an esterification. Not a substitution, addition, etc. Okay? So, esterification are those two things. You take a carboxylic acid, you take an alcohol, and you'll get an ester and water. This is also called dehydration synthesis. Have I written that on your? No. Okay, so it's also called dehydration synthesis. What does dehydration mean?
Missing one.
Right, missing water, removing water, taking away water. So guess what we're going to do? We're going to remove water, we're going to take away water, and we're going to end up it being a product. So let's do an example, ethanoic acid. CH3, C double bond O, OH, and an ethanol. CH3, CH2, OH. Craig, you need to write it down. And we're going to remove water. So can you see a water between the two molecules? Can you create a water? Can you see an H and an OH? Like we did for the acid and alk and base reaction that we just finished. Now here's something a little funny, a little odd. Every other time carboxylic acid has been the proton donor, every other time carboxylic acid has lost that H there, and that totally makes sense because it's an acid, except for an esterification. It's backwards. So in esterification, it loses the OH. An alcohol loses its H. It has to do with bond strength. So it's just, this is the more favorable way. This is the weaker bond combination of breaking. So these two come together, and they form my HOH. Okay? And then I can connect this carbon, which is now missing something, onto that oxygen, which is now missing something. So I end up going CH3, C double bond O from the carboxylic acid, and then O, CH2, CH. 3 from my alcohol. So that came from the alcohol, and that came from the carboxylic acid. And that is an ester. Okay? And to name it, which we'll cover in the next little section, we take, but it's nice to put a name to this right now, I suppose. Oh, I've got it already named. You take the alcohol bit and you make it a branch. So you put YL. So this came from ethanoic acid. So it becomes ethyl. And ethanoic acid, or pardon me, it came from ethanol, so ethyl, and ethanoic acid, so ethanoate, and water.
Sorry, what makes it go to ethanol?
I'll show you some more examples and we'll scroll down. Okay, so maybe. So in your ester section then, bless you, if I can get there. There we go. Okay. Okay, so what is the functional group of an ester and what is the general formula of an ester? I don't really know what I meant when I typed that because they're kind of the same thing. Okay, so we'll just put one answer down for both things. You have to have this C double bond O in the middle, part of which came from the carboxylic acid and part of which came from the alcohol. And then here's that R group for the alcohol. So do you remember that the alcohol's functional group was ROH? Okay, so here we have ROH, but we got rid of the H when we were making the ester. Are you okay with that? And the carboxylic acid's functional group used to be, or general formula I mean, RC double bond O OH, right? But we got rid of the OH. So I need to still put an R there, RC double bond O. But do those R's need to be the same? No. So we can't call them the same symbol, because then that means the same thing. So we use this thing called R prime. So one's R and one's R prime, which just means they're both hydrocarbons or hydrocarbon derivatives, but they're not necessarily the same. Okay? So you might have seen that in math. Yeah? Something and something prime. Okay. Everybody okay with that? How is an ester made? You tell me now.
It's just Esterfication.
How is an ester made? Quick and brief. Dehydration synthesis, that's a good one to put down.
Condensation.
Condensation polymerization. Condensation polymerization is obviously forming a long, long chain by taking out water. What do I need to make an ester?
Alcohol and carboxylic.
Good. An alcohol and a carboxylic acid. Okay, so then dipping down into the how is an ester named. So an ester's name comes from the alcohol and carboxylic acid that it came from. So the first thing you're going to do is identify which end came from the alcohol and which end came from the carboxylic acid. Then you take your alcohol name, you drop the O, and you add YL because it becomes your branch. Remember, you know how all our branches, no, not all our hydrocarbon branches end in YL. Methyl, ethyl. So we're going to take our alcohol and make it a YL. Now these branches could be weird. They could be methyl propanol, right? And then it becomes methyl propol. So we could have a branch of a branch all of a sudden. Okay.
So you drop the like the N too, or would it be methyl propyl or propanol?
Prop,
Do you know what, does that make?
we would take propanol,
Mm-hmm.
drop that and put YL.
Okay, so you like close up.
Propanol. So you're right, it's not propyl anymore, like as if it was a 3-chain coming off. You're right, it is named slightly different than those branches were before. Yes, good observation. Then you take the carboxylic acid name and you drop the oic acid. It's going to become our chain or our main name at the end, and we add O8. Okay? So, for example, you see this compound. You need to identify which one came from the alcohol. So you look for the oxygen, and it's whatever carbon is attached to that bit. They might flip that diagram for you. Okay, so it's not always the end. Could be the beginning. But it's find the oxygen, the carbons that are attached to that oxygen are the alcohol. Okay? And that alcohol was called methanol. Oh, interesting. Hold on. No, we dropped the ANOL.
Okay, so you did say propyl and then,
Yeah.
so.
But then I confused myself in the middle of my sentence. Nope. We dropped the ANOL. So we changed methanol to methyl. And what was this carboxylic acid called? Propanoic acid. And so then it becomes propanoate. So try this next one. Find the alcohol, name it, change it. Find the carboxylic acid, name it, change it. Okay, so this was the alcohol, and what was it called?
Thank you.
No,
That's the
that's the methanol.
That was ethanol, right? So what do we call it now? Ethyl. And here's the carboxylic acid bit. And what was that called? Butanoic acid. And so I name it now butanoate. Okay? So drawing propyl methanoate. Propyl is from the alcohol. So, and it has 3 carbons, 1, 2, 3, and an OH. And methanoate would have looked like this. And so that's it. And that's H2, and that's H2, and that's H3. And if you wanted, you could have written it like this. And it would be the same thing. Okay, yes? I've got an activity that we're going to do. It involves either ripping or using scissors. So if you've got scissors, you can get them out. And you are going to make some esters by this.